start the second talk given by Wolfgang Schmidt. And the title is Counting Matrices with Integers Entries and Sublattices of Z to the N. Please, Wolfgang.
I feel honored and pleased to have been invited to this institute. Especially, I got help and advice from Purushottam and Shauli, but I should also mention Tanga, who helped me here with the PowerPoint, but we'll see if I really was a good enough student to learn it. But also, my hearty congratulations to Ram for your birthday. All right, so it's 15 years ago, I wrote an article called On the Distribution of Sublattices of Z to the M. And it turned out that this work was used, it had applications on Frobenius numbers. And this was one of the reasons why I turned back to these questions. However, before dealing with lattices, it is best to deal with matrices. So here we are dealing with matrices, and so we deal with a set X, capital M, lower n, of matrices with m rows and n columns, and rank n, with n of them satisfying these conditions. So this then consists of matrices capital X with columns x1 through xn, which then lie in Rm and are linearly independent. Well, when we say we're counting matrices, it's well, that looks easy enough, right? There's m times n entries, and it should be easy to count. However, we make our life a little bit more difficult. So suppose you have this n tuple of points in m-dimensional space, then it's an easy exercise in linear algebra to do the following. Write the first one as a constant times a unit vector h1 of Euclidean norm 1. Then the second one will be two sumlets. One is a multiple of x1 and the other orthogonal to the first vector. So some coefficient x1 2 times ch1 plus some coefficient y2 times ch2, where you may assume that y2 is positive. So you have this picture, the constant c is positive, y2 is positive, and the vectors h1, h2 are orthogonal to each other. Their scalar product is 0, and both of them have norm 1. Okay, so now, in other words, well, you have, when you continue this, you have this whole array of relations where the y's are positive and the scalar products hi, hj equals the Kronecker symbol. Now, I won't go into this, but it is a trivial exercise from this that you can write the matrix X in this following form: a constant C times H times Z. Maybe here I should say Z, I don't know. In America it's Z. So CH, Z. Well, again, now the H is in tuple, lies in this space of matrices. However, the inner product of hi, hj is again delta ij. And Z turns out to be the matrix which is written below. And the x's are real numbers, but the y's are restricted to be positive. Now, as many of you know, these matrices make up what is called the generalized upper half plane. When n is 2, you have just x1, 2, y2. If you write this as x1, 2 plus I, y2, you get the complex number in the upper half plane. Anyway, so you can write it like this. So now, we want to I mean, there were two ingredients in a sense. There were two ingredients in a sense, namely, no. Yeah, but two ingredients. On the one hand, we have this. No, what is going on? On the one hand, we have H in this set that we call OMN, and then Z in the generalized upper half plane, and we want to introduce measures in both of these things. So let us start with the upper half plane, the generalized upper half plane. When M is a matrix in GLN of R, and we multiply Z on the right by M, well, then we can do just what we had. We said every matrix, this in N by N, any matrix is a constant times some H as before, and times Z, which lies in the upper half plane. But of course, it will not be the same Z as the left, so let's call it Zm. So you have here this map from Z to Zm, and this gives an action of this group GLNR on the generalized upper half plane. Also, GLN of Z acts on this. After all, it's a subgroup of GLN of R. And let capital F be a fundamental domain for the action, for this action. So this is a subset of the upper half plane. Now, we are interested in the measure mu on the half plane, which is invariant under the action we just explained, and has measure 1 on every fundamental domain. Well, as it turns out, it can do it as follows. I mean, if you have your Z in the upper half plane, take the columns, right? Take the columns, but don't write down all the zeros. That S is just the top of the column, Zi, X1i, X1i, X2i, Xi minus 1i, and Yi, and let this Zi just be what you would expect as a product of all the D's of the components, dxi1, dxi minus 1i, dx, and then if for a subset, a suitable subset of the upper half plane, let's say the measure mu0 of d should be exactly this. So it's basically what you would expect it, dz2 up to dzn. However, there's a denominator by 2 squared up to by n squared. Now, for the standard upper half plane, it's just dx dy over y squared in the denominator. So this is a generalization. Now, I call this mu0 of t because this is the first thing that one thinks about, perhaps. Now, to get it to have the correct value on a fundamental domain, you have to multiply by some constant. And I failed to write down this constant, but then you get this other. So far about the measure on the upper half plane. But now, also, very simple to introduce a measure of OMN, namely capital OMN. I mean, these are really M by M matrices within the products of the columns, the conical symbols. So these are, that's really the matrices of the orthogonal group. And so let omega is just the Haar measure of this group. Let pi be the projection from this orthogonal group to OMN. It's easy, you just take this whole M tuple and end at Hn, H1 through Hn, and parentheses missing, but otherwise it looks okay. So, and then one defines omega Mn of a subset E, when E is a subset of OMN, it's just the omega of the pre-image of it under this projection. Okay, so this is a good measure on OMN. And another definition that we need is the determinant. Well, I did define the determinant of this matrix to be the determinant of the lattice with basis x1 through xn. And the determinant of that lattice, we could say is the volume, is the n-dimensional volume of the parallel pipe spanned by these points. Of course, I realize that it is more modern to call it let's see anyway, okay, let me stick to the old notation, okay. So, and in fact, I mean, if you don't like the talk about matrices, about the term lattices, I mean, we could take the exterior product of these points and take the norm. Okay, so much about the determinant of a matrix, it's the determinant of such a matrix. Okay, so now it's time to make some statement. So suppose D is a subset of the upper half plane, and E is a subset of this set OMN. Then let S, D, E, T be the set of all matrices C, H, Z, with Z in this subset of the upper half plane called D, H in this set E, and the determinant T. Well, then the following is true. I call this a theorem here. Well, okay, maybe it's not hard enough to be called a theorem, I don't know. So anyway, the volume of this thing is some number, VDE times T to the M. Now, that makes sense because it's easily seen that if you take T is 1, if a capital T is 1, and then replace it by T, that means you have a dilation of your set by factor T to the 1 over n, T to the exponent 1 over n. So, and since we are in dimension n times m, these matrices lie in a space, then the factor would be T to the m. So, I mean, okay, so that would be the volume. And this constant in front, well, in view of what I've said already, it's maybe not surprising. It's some constant depending on m and n, and the measure of D times the measure of the set E. Okay, so you could say, well, now come on, this is just an integral or something like that. This is not number theory, right? This is, but so we have to work more. So define n of this set to be the number of integer matrices in this set, and okay, and capital P, the number of primitive matrices in this set. So we have to define what do we mean by primitive matrix. When an integer matrix is called primitive, if you can put it this way, if the lattice with basis x1 through xn is primitive, but if you don't know what that means, one has to explain it a bit better. Namely, it is primitive if it contains all the integer points in the subspace it spans. So if it takes a subspace spanned by x1 through xn, then the lattice with basis x1, xn of all the integer points on its array will be integer multiples, which is not true otherwise. Okay, so now is a theorem on this number. So let D and E be nice sets. Let's just say nice sets a moment. Then as T goes to infinity, you have an asymptotic formula. And of course, maybe it's not a surprise because n, d, etc., this number is asymptotical to the VDE times T to the m. That's exactly the volume, right? I mean, usually if you have a domain in some space, you hope that the number of integer points is close to the volume of this set. And this is in fact the case. Now as far as the primitive ones, you have something very similar, except this factor in front is the one as before, except divided by the product of some zeta factors, z to the m, z to the m minus 1, etc. Now this again should perhaps not be such a surprise, because if you count, for example, primitive integer points in a ball, right, that is the same as counting all integer points, but just divided by some zeta function. Okay. Now, nice. Well, for example, if you assume D and E as what's called semi-algebraic, that is to say defined by finitely many polynomial inequalities, f less than 0 or less than equal to 0, would be called a semi-algebraic set. Okay, so let's stop it there. So why do I want? Yeah, okay. Yeah. So, okay, so these are asymptotic form. However, I'm interested in some error terms. I mean, analytic number theories will be happy to hear there are some error terms that we could consider. And, however, to do this in generality sometimes is a bit tough, or it's hard to get good error terms in generality. So I give an example of how one takes some special case where one can do better. So let alpha be such an n-1 tuple of, there should be non-negative numbers, alpha 1, etc. D of alpha is a subset of H, where the yj plus 1 over yj is at least alpha j, so they can't decrease too much, and the xij's are bounded as here, and the x1j, it's a little bit more. So by the way, y1 here didn't occur in the statement of the upper half plane, but one should say y1 is equal to 1. Okay. So when n is 2, then this could look just like this, right? In the upper half plane, and it is domain on the top of the y is at least y1. And I'm introducing this context two numbers. The omega of alpha is a certain product of powers of the alphas. Omega tilde alpha, another product. You don't have to worry about it too much, but okay, there are these products. And then it turns out that the measure of this set is equal to some constant again. My constants are not always the same, they vary, times omega alpha, so that gives you one reason why this may occur. Now the second remark may be a little bit more obscure, especially since there's some mistake in this write-up. 2 days ago, I was asked to hand this over to make such good copies to show here, and I hadn't thought that I should have double-checked my notes before I gave it away, but okay. So I have in tuple sigma, a tuple sigma is sigma 1, sigma 2, sigma n, and we call E to be of type sigma if the following holds. If the elements in this set are as follows. The H1, of course, H1, well, it has no one. It lies in a sphere. It lies in a sphere in m-dimensional space. So H1 should be, it will be restricted to a set of spherical measure sigma 1. Okay, so H1 should be restricted to a set of spherical measure sigma 1. Then given H2, when given H1, when H1 is given, then H2 is restricted to a space of dimension m-1. More precisely, the sphere lying in m-1 dimensional space. And the condition is that given H1, this H2 is restricted to have spherical measure sigma 2, see, etc., etc. And then such a set has this measure, the product of the sigmas, sigma 1, sigma 2 through sigma n. It's a fairly strong restriction, but one can get around it a little bit in application. So now, with this restriction, we have some theorem, namely, you have again your sets, and we assume E to be a sigma set as just explained, and I shouldn't have this, we don't talk with D, we talk D alpha, the set that I explained, D of alpha, okay. So this is equal to this V, as we had before, times T to the N main term, plus an error term. Good, at least we have an error term, and that has omega tilde of alpha, times this pi of sigma again, and T to the N minus in exponent N minus 1 over N. So that's a reasonable error term, and this primitive ones, it is rather similar. I haven't written down what this new V tilde would be, but it is the one before just divided by the zeta factors. And here it's the same in the error term, except there's another factor log T, which doesn't bother us too much. And the constant depends on the type of the sigma algebraic set. I mean, E is supposed to be sigma algebraic set. I mean, if it's defined just by quadratic inequalities or so, you get some good bound. Okay. Well, so far about matrices. Now, in a sense, the whole point was to get to lattices. So let's look again at sublattices of Z to the M. Of course, Z to the M is a lattice. It's a lattice of rank M, right? A free group of rank M. And we take lattices of rank N again. Now, in general, even if they're not integer, if they're not in Zn but in Rn, you can say the following. So such a lattice has a basis, right? So a free group generated by some basis elements which make up a matrix X. But the difficulty is that X is not uniquely determined by the lattice, of course. When N is bigger than 1, especially, there will be infinitely many bases. So how does this connect with what we said about matrices? So one should pick out some particular basis. Now again, I don't seem to have written this down here, but if you demand that your that the basis that is Z, I mean the variety vector, if you write a matrix X equals C H Z, that Z lies in a given fundamental domain. If you demand that, then the Z is determined by the lattice, and the Z is determined by the lattice. So it's best then to take subsets D of the fundamental domain, which, let's see, maybe I had something. See, I missed this page. I thought, I missed this page. Okay, yeah. So they have these lattices, and this is if Z lies in a fundamental domain, which is not written here, then Z is determined by the lattice. Okay. Another thing that we wanted was the Grassmann variety, GMN of n-dimensional subspaces of Rm. And there's an invariant measure on this space invariant under orthogonal maps. Now, suppose now you have a D in a fundamental domain and some subset of G of n, some set of n-dimensional subspaces, then that SDGT consists of lattices which have a basis as written on top, X is CHZ, with Z in this D, which lies in F, and if S of lambda is a space spanned by lambda, it should be in this set G. Of course, you see, in a way, you could argue like this. If you write, I mean, the D determines, in a way, what you may call the similarity class of the lattice. I mean, the D is an intrinsic, determines an intrinsic property of the lattice, whereas the H determines the space in which it lies. And of course, the subspace in which your lattice lies is also very important. Now, the volume of this set is some constant, again, it's a different constant from before, some constant depending on D and G times T to the N, which in this case, not surprisingly, is a multiple of mu of D times the measure rho of G, okay. And so now we are ready for our theorem that was already here in a moment ago. So now we need G to be a semi-algebraic set, and L, the L here refers to lattice, I guess. So NLDGT is asymptotic to this and similar for the projected. Now, by the way, I had this, as I said in my work of 15 years ago, I should remark that Rilke in the 50s and then later Massa did this for the case n is equal to 2. N is equal to 2 using modular forms. So I'm glad I can mention modular forms here. Okay. But I mean, my method is, in a way, more elementary, just bare hands. Yeah, okay. Now, what about explicit bounds? So again, now I want to restrict something to get these. Let the lambdas be successive minima of your lattice. I suppose you know, Minkowski's theory, successive minima, lambda j being the largest one, such that if you blow up the unit ball by the factor lambda j, it will contain at least j linearly independent lattice points. So the order lambda 1 less than equal lambda 2, etc. And that then these lambdas determine in a way the shape of the lattice. I mean, if lambda 1 is about lambda 2, the lattice points may seem like the vertices of squares, more or less. Otherwise, if lambda 2 is much bigger than lambda 1 in 2 dimension, the lattice points will be sort of vertices of some stretched rectangles. Anyway, so L should be the set of lattices where this inequality holds. So, of course, lambda m is at least as big as any of these lambda j's in the denominator, but we want it even bigger, this product even bigger. Okay. And okay, good, we do get a result here. The number of such, I restrict myself now somewhat. Okay, so we make a very simple assumption. G should just be a non-empty open set. Non-empty open set of subspaces. Then the number here, P of S, L of L, etc., is bounded below. Is bounded below by this quantity. So, of course, you have your factor T to the N, and some constant depending on G, L to the minus 1, and add an error term. Okay. So that's a lower bound. Now, it's maybe not too fancy, but you'll see I like to know about primitive lattices anyway. Now take another rather special case, but suppose n is equal to n minus 1. Okay, you take sublattices in a space of codimensional 1. Now, and we take subspaces as follows. Well, such a subspace of codimension 1 will be defined by a linear equation. It's written down here. But the a's are fixed coefficients and the coordinates, the sum of these a1, xi1 is equal to 0. And we take the set of subspaces where the ai is bounded by delta I times the maximum norm of A, that's the norm of this vector A1, A2, AM. And we said delta is the product of this little capital delta. Now, by the way, this set G, I mean, it has a measure, a rho of G, which is essentially the order of magnitude delta. Okay. So then it's the theorem that here you restrict your subspaces to a very small set, if these deltas are small, right? But then you get, of course, a beta bound too, because you have this factor delta here, the factor, in front of the t with m, and again some error term. By the way, of course, you know, how come you get this, this doesn't seem to connect with what you told us before about the lambdas, but one first would have to deal with L of alpha rather than this space here, rather than what we call L of capital L. And so there would be some previous work that you need to do this, etc. But never, so okay, now I'm finished with lattices. How much time do I have left? Okay, 7 minutes, yeah. 7. 8. Oh, thank you, good. Can I negotiate? 9? No. Okay. So now we come to Frobenius numbers. As many of you know, I mean, if an n tuple of natural numbers now, which are relatively prime, then capital F of A is a so-called Frobenius number, is least such that every b bigger than f of a can be written as a linear combination of a1 through am with integer coefficient integers x1, xm, which are non-negative. Okay, so that's the definition of Frobenius numbers, and if the components are relatively prime, this number exists, otherwise it wouldn't work. So what are some old results? For example, when n is 2, there's something due to Sylvester in 1884. Well, it's an explicit expression. I think he just maybe this is a little exercise or something. Okay. Now, when n is bigger than 2, there does not seem to be a formula, a close formula for this thing. And when asked what is sort of the average behavior of the Frobenius number, and Arnold, starting in 1990, made some conjectures about this, namely that on average, it should be some factor, n-1 factorial to some exponent, times P of A, where P of A is the product of the m's with exponent 1 over n-1. Okay, so this is what Arnold conjectured, and in fact, his conjecture is at least is true that it is essentially a lower bound for f of a, because it was proved in 2007. You have this bound with some little subtracted, but it's Erbish and Graham give an upper bound. But now to come back to Arnold's conjecture, I mean, we know that already by the second line here, f a over p of a is above some constant, but how often is this much bigger? How often is the Frobenius number much bigger than the value here? Now, to make sense of this, we have to have some set of n tuples that we can talk about and average about. So take the simplest we can think of, g of t, like capital T is given, consists of all n tuples which are relatively prime and which have, let's say, maximum norm not bigger than t. Okay, so the line is cube here, and despite of asking them to be co-prime, you see the cardinality is essentially t to the m. Okay. And now let capital N of capital T, little t, be the number of n tuples in this set where you have this inequality, the start inequality where f a over p of a is bigger than t. Okay. And Markov in a difficult paper showed that given a little t, at least one, then as capital T goes to infinity, this quotient has a limit that's called capital psi of t. All right? It didn't say what the limit was at this point. On the other hand, Bergheim and Sinai showed that, in fact, if you take this quotient here, capital N of t over g of t, it is less than, basically less than a function of phi of t, where phi of t is a function, phi of little t is a function that goes to 0. So in other words, if you make a little t large, this quotient on the left will be small. There will be few of the elements in our comparison with g of t where the Frobenius number is bigger than expected. I mean, in precisely this like this, 1 plus little o1, of course we're talking for this to go for large t, okay. On the other hand, Aleph and Henk, and then Aleph, Henk, and Cambridge showed that you may take a function phi of t equals little t to the minus 2 and to the n with exponent n minus 1 over n minus 2. Well, so good. It goes to 0. We have some precise result. Of course, you still have this with little o1, so it's asymptotically true as capital T goes to infinity. It is not the bound which is uniform for all little t's or anything like that. Then Strömbergson last year had a published paper which gave some results for Markov's psi, and it is t to the minus n minus 1 and the exponent with some numerical factor. By the way, this numerical factor is not the same one with Arnold had, but okay. And yeah, he also showed that this quotient is less than, and now there is an explicit constant here depending only on m, and only on m t to the minus n is 1 or 2 some log. So this is much better than the phi we had before, but it had only n minus 1 divided by n plus 1. By the way, this work of Arendt and Henk, etc., depended on my work that I had mentioned earlier on the distribution of sublattices of E to the m. And the same is true of this last estimate due to Strömbergson. Okay. So now what we have is something better, namely this quotient is essentially bounded by something we call m here. M is t to the minus n minus 1. So there's the last exponent was n minus 1 over 2. There's t to the n minus 1 times some log factor, and there's some error term here too, but the main term is like this. But there's also a lower bound, so there are some a's where the Frobenius numbers are large, relatively large. And you see the factor t to the minus n minus 1 is the same. And it has a corollary that if I take f away divided by the expected p away to the alpha and take the sum over all a's in our set, g of t, this sum is less than capital I of t, g of t, which means, of course, that on average f of t over p of t is bounded, it's not large. And I can do this for alphas which are certainly less than n minus 1 half. I can do a little bit better. By the way, I should say that when Arif and Henk also claimed something of this kind, maybe this alpha is equal to 1, but actually they were not, their argument was not quite solid because they only used the asymptotic formula, but one needs some error terms to achieve this. Okay, now, how does one try to prove something like this? So we may say that A's are ordered A1 less than or equal to Am, and now let capital lambda of A be the lattice in Rn, which is exactly the one which has this equation, A1x1 plus AMxn. I mean, it lies in this subspace and consists of all the integer points in this subspace, also solutions with integers. So here I tried to draw a picture of this space and maybe some lattice. And of course, the rank of this lattice is n, and the determinant is not hard to see, is essentially the Euclidean norm of the vector with components a1 through an. Now, if you see, I mean, the an should be bigger than a1, but if an is about a1, then p of a is about an times am to the 1 over n. And Cannon in 1992 showed the following, that this Frobenius number f of a is of order of magnitude, and maybe I should, let's look right to the last line, is of order of magnitude an times the nth minimum of this lattice lambda a with respect to the bar of radius 1. So forget about this written on top. So f of this order of magnitude. So here we have some connection now with the lattice, right?
Well, I'm afraid.
The time is over?
Yes.
Yes. Well, okay. So let me just say that the point now is we have to count lattices. We have to count lattices whose minimum, whose nth minimum must be between certain bounds. And I mean, after what I said at the beginning, I think it's reasonable to assume that possibly what we had shown here would have the desired consequence. And I want to point out that actually the harder part in a way is to get the lower bound, because these lattices, they contain all integer points in its space. They're primitive lattices. So we have to give a lower bound for the number of primitive lattices. Okay, so sorry, I stop here.
Okay, thank you very much. So maybe we have time just for a short question. No? Okay, thank you. So we will resume in just 1 minute. Thank you very much.
So.